In this program, I want to take a look at Born-Haber cycles and lattice enthalpy. Let's begin with lattice enthalpy. Lattice enthalpy gives us a measure of the strength of the ionic bond. It's defined as the measure of the energy required to convert 1 mole of the ionic solid into its gaseous ions. We would write this in a chemical equation the following way. The lattice enthalpy depends on a couple of factors. First of all, it depends on the charges of the species involved in the ionic bond. So we'll compare here sodium fluoride to sodium oxide. Oxygen has a -2 charge, fluorine -1. So oxygen having a greater charge should pull the positive ion closer, creating a stronger ionic bond. This should then result in a greater lattice enthalpy, and we can see here by comparing them. So increasing the charge of either of the ions or both of them will increase the lattice enthalpy. Another factor is the radius of the ions involved. Let's here compare sodium fluoride with sodium chloride, chloride having a larger ion. That would create a greater distance between the centers of charge, which should weaken the electrostatic attraction and lower the lattice enthalpy. And we can see that here. The Born-Haber cycle is a technique to measure the lattice enthalpy using a series of steps. These steps we can find data for. So here's what the cycle looks like. We'll break it down first of all by starting with analyzing the information highlighted in red. Here I want to turn sodium oxide into its gaseous ions. That's the lattice enthalpy. So I want to start here and finish here. Now I'm going to consult a series of steps, and I've highlighted them here and given their values. Let's go through them one at a time. To convert solid sodium and oxygen gas into sodium oxide, that's called formation. I want to go the other way. I want to reverse that direction. Hence you see the negative sign in front of the -416, where -416 was the heat of formation. My next step is to take sodium solid and turn it into sodium gas. And there's 2 of them to do that with. Hence you see the 2 times 107. My next step is to break the bond in the oxygen gas, that double bond, to create a single oxygen atom. That data we can find in our IB data booklet. It's found in Table 12, bond enthalpies. This is the related information we need. You'll notice here it's 498, but recall that that's per mole of bonds broken. So if I break an oxygen-oxygen double bond, I end up with 2 oxygen atoms. So in this case, I have to multiply it by half because I need only 1 oxygen atom. In my next step, I'm going to turn sodium gas into a sodium gaseous ion. That requires the removal of electron. That's what we can find, again, in a different section of our IB data booklet, Figure 9, which gives us periodic properties. In the top left corner is the first ionization energy of sodium. So to do that, again, I have 2 sodiums present, so 2 times that 496. The next step is giving oxygen an electron. That you'll find also in that section of the IB data booklet. But there's 2 values here, because oxygen tends to get a -2 charge. The first electron is an exothermic process, marked here by step 5, where we go down 141, and the next step we go up 753. So I've gone from my start to my finish. All I have to do now is add up these values, and I get 2,482 kilojoules per mole as the lattice enthalpy. Let's look at another example. Determine the molar enthalpy of atomization of element N using the Born-Haber cycle shown below. So what we're after is this value right here, to turn M solid into M gas, using the information presented in the cycle. I want to start here and finish here. So my first step is to go down 450. My next step is to go up 1650. And then I'm going to go up. So that means I have to reverse that sign and make that positive 160. My next step is to go down against the arrow, so I have to make that negative 400. And similarly, I have to go down in the next step, down 120. That then takes me to my finishing position, just a different path. I add these values up, and I get the heat of atomization is 840 kilojoules. Thanks for watching.